Your code looks sequential. Line 1, line 2, line 3. You assume the CPU runs it in that order. It doesn't. And that single misunderstanding explains why modern CPUs are so fast, why micro-benchmarks lie, why memory ordering exists, why speculative execution caused Spectre, and why performance tuning is often counterintuitive. Let's start with the illusion. When you write simple code, compute something, store a value, compute something else, it looks like a list of steps, one after another, clean, deterministic. But the CPU does not see a list of steps. It sees dependencies, and more importantly, it sees independence. If two instructions don't depend on each other, why would the processor wait? That question is the foundation of out-of-order execution. Not randomness, not chaos, dependency-driven execution. Now here's the real problem. Modern CPUs run at several gigahertz, a few tenths of a nanosecond per cycle. Main memory? Roughly 100 nanoseconds. That's hundreds of cycles. If a processor executed instructions strictly in order and hit a cache miss, it would stall for hundreds of cycles doing absolutely nothing. At gigahertz speeds, that's catastrophic. Out-of-order execution exists because waiting is unacceptable. Early processors were simple. Fetch an instruction, decode it, execute it, write the result, move to the next instruction. If one instruction stalled, everything behind it stalled. Imagine a grocery store with one cashier. If one customer has a problem, everyone waits. That's in-order execution. Simple, predictable, slow. Now imagine a different store. Multiple checkout lanes. Customers can move forward as soon as they're ready, as long as they're not waiting on something. That's the insight. What if the CPU could look ahead, find instructions that are ready, execute them early, and then commit their results in order later? Execution order doesn't have to match program order, as long as dependencies are respected. That's out-of-order execution. To understand this properly, we need to talk about dependencies. There are three types: read after write, write after read, write after write. Only one of these is truly fundamental. Read after write is real. If an instruction needs a value produced by a previous instruction, it must wait. The other two are artificial. They exist because of limited register naming, and solving that limitation changed CPU history. Suppose one instruction writes to a register, and a later instruction also writes to that same register. Architecturally, they look connected. Physically, they might not be. Modern CPUs solve this using register renaming. You think the processor has maybe 16 registers. Underneath, it may have hundreds of physical registers. When one instruction writes to a register, the CPU assigns it a physical register. When a later instruction writes to what looks like the same architectural register, it assigns a different physical register. Now those two instructions are independent. False dependencies disappear. Only true data dependencies remain. This is where out-of-order execution becomes powerful. Once instructions are renamed, they enter a structure called the reorder buffer. This is the heart of the machine. Instructions enter the reorder buffer in program order. They execute when their operands are ready. They may finish in a completely different order, but they retire in program order. That retirement step is critical. Architectural state, what software sees, must appear sequential, even if execution was not. This preserves the illusion of sequential execution while allowing massive internal parallelism. After renaming, instructions are placed into reservation stations or issue queues. These structures monitor operand readiness. The moment all inputs are ready and an execution unit is free, the instruction issues, not when it appears in the original sequence, when it's ready. Imagine a load instruction that misses the cache. It might take hundreds of cycles. In an in-order processor, everything behind it stalls. In an out-of-order processor, independent instructions keep flowing. Arithmetic operations, other loads, branches, multiplications. The execution units stay busy. This is not reducing latency. It's hiding latency. That difference matters. Modern CPUs have multiple execution units, multiple integer ALUs, floating point units, load and store units, branch units. Without out-of-order scheduling, most of that hardware would sit idle much of the time. Silicon would be wasted, power would be wasted. Now introduce branches. When the CPU encounters a conditional branch, it does not stop and wait for the condition to resolve. It predicts the outcome. It speculatively executes instructions down the predicted path. If the prediction was correct, it keeps going. If it was wrong, it rolls back. The reorder buffer makes this possible. Because results are only committed in order, incorrect speculative results can be discarded before they become architecturally visible. Out-of-order execution and speculation are deeply connected. Now let's talk about limits. Out-of-order execution extracts instruction-level parallelism, but only if it exists. If your code is a long dependency chain, where each operation depends on the previous one, there's nothing to parallelize. One result feeds the next. The hardware cannot break true dependencies. It can only remove artificial ones. Memory complicates everything. When the CPU sees a load, it doesn't always know whether it depends on an earlier store. If a store writes to one address and a later load reads from another, are they independent? Maybe. Maybe not. The processor often speculates that they are independent and executes the load early. If later it detects that the load should have waited for the store, it rolls back. This is memory disambiguation. Another layer of speculation. To support this, processors use store buffers and load queues. Stores enter a buffer before they update the cache. Loads check that buffer to see whether a more recent store to the same address exists. If so, the value can be forwarded directly. That's store-to-load forwarding. All of this logic exists to keep execution units busy. But it's expensive. Reorder buffers contain hundreds of entries. Physical register files are large. Dependency tracking networks must wake up instructions when operands become ready. All of this happens every cycle. At gigahertz frequencies, the power consumption is enormous. The verification complexity is enormous. That's why small embedded processors often use in-order cores. They are simpler, more predictable, more power efficient. Large server CPUs go aggressive, wide issue widths, deep buffers, heavy speculation, different design goals. Now consider security. Speculative, out-of-order execution leaves microarchitectural traces. Even if incorrect speculative results are discarded architecturally, they can influence cache state. Attackers realize that they could measure timing differences and infer secrets. That's Spectre. Without out-of-order execution and speculation, that class of attack would not exist. Performance and security are intertwined at the microarchitectural level. Now think about benchmarking. You test a single instruction. It appears fast, but real programs are mixtures of dependencies, branches, cache behavior, and resource contention. Out-of-order execution may hide latency in one case and amplify contention in another. Throughput of an isolated instruction does not equal performance of a real workload. Mechanical sympathy matters. If you write code with fewer dependency chains, better memory locality, and predictable branches, you allow the hardware scheduler to extract more parallelism. If you write long serial chains with unpredictable branches and cache misses, you restrict it. Compilers help by reordering instructions, unrolling loops, and exposing independent operations. They are cooperating with the hardware scheduler. Now zoom out further. Out-of-order execution means the CPU does not strictly execute instructions in source order. Memory consistency models define what ordering must appear visible to other cores. Sequential consistency enforces a strong illusion. Total store order allows certain reorderings. More relaxed models allow even more freedom. Memory fences exist to constrain what out-of-order execution is allowed to expose externally. Without understanding out-of-order execution, memory models feel abstract. With it, they make sense. Within a single core, out-of-order execution extracts instruction-level parallelism. Across multiple cores, cache coherence protocols coordinate shared state. Now you have speculation, store buffers, invalidation messages, and coherence traffic interacting. That's why scaling is hard. Out-of-order execution exists because waiting is unacceptable. Modern CPUs are latency machines trying to behave like throughput machines. They rename registers. They track dependencies. They speculate aggressively. They execute instructions whenever possible. and they retire results in order to preserve the illusion that everything happened sequentially. Software continues to work because that illusion holds. If you are building high-performance systems, databases, trading engines, game engines, runtimes, operating systems, you are programming a machine that does not execute in order. It speculates, it rolls back silently, it hides latency when it can. Understanding this changes how you think about performance. Out-of-order execution sits at the pivot point between hardware and software. Below it, pipelines, execution ports, cache hierarchies. Above it, memory models, concurrency primitives, distributed consistency. It is the mechanism that makes modern single-thread performance possible. And once you see it, the sequential illusion never quite looks the same again. From here, the next logical layer is deeper into reorder buffers and scheduling logic, or into memory reordering and consistency models. Because once execution is no longer strictly sequential, the abstraction stack above it changes. And that's where modern systems engineering really begins.